Hi everyone, and welcome to our third and final lesson on simple circuits exercises. I've drawn a circuit here, and this is the final circuit we're going to work on because I feel as though if you can solve this circuit, there's very little which should challenge you in Year 12 physics. The way we're going to solve this circuit is by using a bit of general explanation of what I like to call the lazy charge. And that's a charge that doesn't want to do more work than it has to. And if it's made to do more work, will do so a bit unwillingly. So, looking at this circuit here, this resistor ought to pose no problem to anyone because it's simply in series with the battery. But this section here does and has posed a real challenge to students in the past. Is it series? Is it parallel? Where's the charge going to flow? Which direction is the charge going to flow? That's the kind of thing we're going to work out before we find the total resistance of the circuit. So the end goal by the end of this lesson is to have found the total resistance of the circuit, the current going through the battery, the voltage through each component, and also the current through each component. First of all, this section here. Let's figure out what exactly is going on, whether it's series or parallel, by using the path of a charge. So the charge comes out of the battery. Really, it would be going this way, but we'll look at it in the terms of conventional current, the flow of positive charge. The charge leaves the battery. It must flow through this resistor here. And then let's look at one possible path that charge might take. Down here, through the lowest resistor, and then to this point here. Now, if the charge is lazy, is it going to want to go this way, in which it gets the quick route back to the battery? Or will it want to go this way, through more resistors and all over the place? Clearly, this charge will want to flow straight out and back into the battery there. It's a lazy charge. It doesn't want to do more work than it has to. Let's look at another potential path a charge might take. Out of the battery, down here, and then up through the 30 ohm resistor to this point here. Will it go through this resistor here and then back around through that one there? Of course not. It'll flow right out through the battery. And then the third path we're going to look at, I'll use purple, is when a charge flows through that top resistor there, back down to here, or even stopping at that top corner. Since it's a lazy charge, it'll want to flow straight out, not go through any more resistors than it has to. There we go. So we have a total of 3 different paths a charge is going to take. That is the clue which enables us to tell you that this section here is made up of 3 resistors in parallel. And the way we know that is this. A charge has only 8 volts to spend on whichever resistor it goes through. If it spends a certain amount on this 3 ohm resistor, it has some voltage left to spend on a resistor of its choice in here. So let's say it has X volts left to spend, using a bit of algebra. Since each path takes the charge through only one resistor here, it has to spend that full amount of voltage it has left on whichever resistor it passes through. In other words, here's the key. Each resistor here will receive the same amount of voltage, which is typical of a parallel section of the circuit. So this is simply 3 resistors in parallel, like so, but drawn in an unorthodox way. So let's figure out the resistance of this section here. 1 over R equals 1 on 15 plus 1 on 30 plus 1 on 60. Which is equal to 60 on 7, or approximately 8.57 ohms. And the resistance here is 3 ohms. So the total resistance of this circuit, we can really imagine it as the 3 ohm resistor there, and then the model from the battery's perspective, it doesn't see these three resistors in parallel, only really sees one resistor of 8.57 ohms, then we complete the circuit. So the total resistance of this circuit here, we can use a series equation. It's 3 plus 8.57, that's 11.57 ohms. Total resistance, RT equals 11.57. So the total current going through the battery, well, the battery has to obey Ohm's law as well, V equals IR. 8 volts equals 11.57 ohms times resistance. So 8 divided by 11.57 equals R, which is equal to 0.691. Whoops, sorry. R was 11.57, so 8, whoops, I've got this all wrong, times I there. I'll change it around. So V equals I, which was the mystery, times R, which was 11.57. So 8 divided by 11.57 is equal to I, which is equal to 0.691 amps. So there's 0.691 amps flowing through the battery. Since this resistor is the only path a charge coming out of the battery can take, there must also be 0.691 amps flowing through this resistor. So the voltage through this resistor is IR, which is 0.691 times 3, which is equal to approximately 2.691 times 3, 2.07 volts. If a charge has dumped 2.07 volts on this resistor here, then the difference between the amount of voltage that it had and the amount it lost is equal to 5.93. So before we said it had X volts left to drop over these resistors here, and that amount, X, is equal to 5.93. So each of these resistors gets 5.93 volts. The final thing we're going to do, I'll fill in this, so we had 0.691, and then VI and II, the individual voltage and current we're working out, is to work out the amount of current through each of these resistors up here. So we had Ohm's law, V equals IR, so I equals V on R, and we have here I must be 5.93 divided by 15, which comes to 0.395. So there's 0.395 amps of current going through that resistor there. The middle resistor, I equals V on R, 5.93 divided by 30, comes to 0.198 amps. And the lowest one, 5.93 divided by 60, is equal to 0.099 amps. And if we add up each of these individual currents, we get 0.691. So this plus this plus this equals 0.691, which is the total amount of current we pumped into this section here, and also the current flowing out. Now the challenge question is how much current is flowing through that section there. This is the last question I'm going to ask. How much current is flowing through this section of wire? Because we can ask how much current is flowing through a wire. We can't really ask how much voltage the wire has because resistance is effectively 0. So voltage equals I times 0. The voltage equals 0. We can ask how much current is flowing through it. The answer is all the current that was flowing through that wire there and that wire there flows into this part of the wire here. So the current flowing through that part of the wire there, I, is equal to 0.198 plus 0.395, which is equal to approximately 0.593 amps. I hope this was helpful, these 3 lessons on simple circuits, and that this has given you more tools to solve these questions when you get assessed on them. And it's almost a guarantee that at some point you will be assessed on a circuit with a battery and a few resistors in it. So good luck.